for me, but of course, I'm quite happy to get the chance to talk with all of you. Thanks everybody for being here. And well, let me tell you a little bit about this research, this work that we did with Rustam, our colleague here, about partial communication. Something quickly. As you can see on the bottom, I'm supposed to have, or we have 48 slides, but that's including the if time allows part. So I think that my main goal today is to be able to explain properly what this idea of partial communication is. We don't need to go through the arbitrary partial communication part, which means that I will try to discuss all the things that are important in as much detail as I can. And also means that if there is any question or something that needs to be clarified in the middle of the presentation, by all means, just let me know. I'm happy to try to make things clear so we can all follow what we are trying to discuss here. So having said that, then let me then start with the presentation. This is more or less the plan, but let me just go quickly through, trying to tell you in a little bit more, trying to tell you which one is the main kind of things that we are interested in. It was already mentioned in this very nice presentation of me, saying that the kind of things that I am interested in is can be summarized in this phrase, logical approaches to dynamics of information. And that means, in a little bit more concrete and precise terms, that we, or I in particular, I'm interested in representing and reasoning about two things. One of them is the information, the different types of information an agent or a set of agents might have. It could be knowledge, could be beliefs, could be preferences, and so on. And for this, we might typically use tools as epistemic logic, as we will do during this presentation. But of course, we are not limited to that. We also like to explore some other ways of representing, again, knowledge, beliefs, or preferences of an agent or a group of them. And the other thing that we are interested in is in representing the actions through which that information, the knowledge, the beliefs, and preferences of the agents might change. And that might include, well, actions as acts of inference or observations, or as we will discuss today, some form of communication. And again, typically we might use ideas and the philosophy behind dynamic epistemic logic, which I will clarify in a second what I mean by that. But as just one of the tools that we might use in general, is just we are interested really in representing different forms of information agents might have and the actions that transform them. That's in very, very few words the kind of things that we are interested in. And zooming in on what we want to discuss, or what I want to talk about, what I want to talk about in this talk is there is already a famous kind of action that has been studied in epistemic logic and dynamic epistemic logic, which is this kind of action through which agents receive truthful information from an external source in a fully public way. Those of you that are familiar with epistemic logic, dynamic epistemic logic, might recognize this as public announcements. So somebody from the outside gives the agent certain truthful information in a fully public way. What we want to discuss today is a somehow related action, but that differs in one very crucial aspect. We will still talk about truthful information. We will still talk about information being shared in a fully public way, but we will focus on information that comes from the agents themselves. So this is not somebody that comes from outside and tells the agents about, for example, a given formula being true. We want to discuss what happens when the agents themselves are the ones that are sharing their own individual information. The main reference is a paper in Studia Logica, and the reference can be found at the end of these slides. So the plan that I have, the plan that we have for this presentation is I'm going to recall quickly the basics of epistemic logic and the notion of distributed knowledge, which plays an important role, and it's a little bit, in a sense, the motivation of all these actions through which agents share their own information. Then I will go into discussing the idea of communication, first warming up, discussing one slightly simpler action through which some agents share all that they know, and then going into our main focus, which is action through which some agents share part of what they know. And then again, if time permits, we will discuss arbitrary partial communication. So that's the plan for this presentation. And then let me go to then presenting the tools, meaning introducing quickly or recalling quickly, depending on your expertise, the ideas behind epistemic logic and distributed knowledge. So in epistemic logic, the idea is just finding a way or having a way of representing different forms of information an agent may have. For this, we have two sides, as in many logics. We have the semantic side, the structures that we want to describe, and then the syntactic side. In the semantic side, the structures with which we will represent, in this case, the knowledge of an agent are the following. We take a set of atoms, which are the facts that the agents might discuss, and we have a finite set of agents, A, B, and C. And these structures, which are known also as Kripke model, possible worlds model, they are nothing but, well, the way that I like to call them, relational models. That's a graph, essentially, with the different relations, with different binary relations in it, meaning we have a collection of points, things that are understood as different ways in which the real situation might be. Each one of those things, each one of those possible worlds corresponds intuitively to evaluation for the set of atomic propositions under discussion. And the crucial component of these models, at least the crucial with respect to the information of the agents, is for each one of the agents, we have a binary relation, which we call an indistinguishability relation, essentially telling us from one point which are the points or the worlds that the agent considers possible. So in this picture, as you can see in the center, we have a world in which both P and Q are true. And if that were the real situation, then our agent would consider that very same world, or agent A, would consider that very same world as a possibility, but also the world on the right-hand side, the one in which P is true. Our agent B, on the other hand, would consider as the only possibility the world on the left-hand side, the one in which Q is true. For evaluating formulas of the language that I will present in a second, or recall in a second, we need not only a model, but rather a pointed model, meaning we need to select among the worlds in this model one that we understand as the one representing the real situation. Those are the models, and an important, well, there are a couple of things that I would like to emphasize about these models. 3 important points. One of them is that even though we use those models for representing the knowledge of an agent, what we are really representing is the uncertainty of the agents. What we really have there is these indistinguishability relations that tells us which are the alternatives each one of the agents considers possible from a given point. And then out of that uncertainty, we define the notion of knowledge. In fact, as we will make precise in a second, knowledge is understood as whatever is true in all the situations that the agent considers possible. So very important, an important first point, in the models, what they represent is not really the knowledge, but rather the uncertainty of the agents. Second point, in particular to this talk, normally in this setting, when you talk about knowledge, you ask for these indistinguishability relations to satisfy additional requirements. And this is so one gets a notion of knowledge that satisfies some standard properties. For example, typically one might want for a notion of knowledge to be truthful in the sense of if the agent knows something, then that something is true. And on top of that, you might want to ask for a notion of knowledge that has these positive and negative introspection properties. If the agent knows something, then she knows that she knows it. And if the agent doesn't know something, then she knows that she doesn't know it. Here in this presentation and in this work, we don't make any assumption about the properties of the relation. So in a sense, the term knowledge is used in a very loose way. Still, if you want to add reflexivity or symmetry as requirements, that's still perfectly fine in our models. But if you want to add transitivity or Euclidicity, which are typically the properties that we connect with positive and negative introspection, then we might have a couple of technical issues along the way. So for the sake of simplicity, then we don't ask for any property of the relation, and we use the term knowledge in a loose way. And finally, even if the relations contain, or the models contain only indistinguishability relations for individual agents, it is still possible to define notions for groups of agents, in particular notions of knowledge for groups of agents in this kind of structures. And the one that is particularly important for us is that of distributed knowledge. So this notion of distributed knowledge has received different names through the history in the literature. It has been called impersonal knowledge. It has been also called implicit knowledge. It is nowadays called commonly distributed knowledge. And the idea of this concept is the following. It is supposed to include everything that follows from the combination of the individual knowledge of the members of the group. So in principle, the agents might have individual information. One of them might know that P is true while not knowing anything about Q, and the other one might know that Q is true while not knowing anything about P. The idea is that if they were to put together everything that they know, then whatever follows from that, that's going to be called distributed knowledge. So in this example that I was mentioning, the agents might have or will have or have distributed knowledge about the conjunction P and Q, even though none of them knows individually that that's the case. So this intuition can be represented within epistemic logic, and the typical way to do that is, I think, a very natural and very nice one, because what one does is to define a relation that is going to stand for the distributed indistinguishability of the agents. And for this, what one takes is, given a group of agents G, we take the intersection of their indistinguishability relations. With this, what we are saying then is that the group, or G as a group, is going to consider possible one alternative, one world, if and only if every agent in the group considers that world as possible, or in other words, if nobody in the group has ruled that possibility out. So that seems natural in these models in which what we are representing is uncertainty, because then the idea of the agents putting together their information boils down to the agents telling each other, look, I already discarded this possibility. We as a group can discard it also, and so on and so forth. So once that we have this relation for distributed knowledge, then one can define a modality that is semantically interpreted in the following way. This modality that tells us the group G has distributed knowledge of phi in a given pointed model, that's going to be the case if and only if in every world that we can reach by the relation for the group, in all those worlds, phi is indeed the case. So this again following the idea of describing or defining knowledge in terms of uncertainty. It's just that now we are defining distributed knowledge in terms of the distributed uncertainty of the set of agents. Now, this has some drawbacks. This is not, this has some properties that might not be the ones that we might want to have. In particular, this definition of distributed knowledge in the literature doesn't quite fit the intuitive definition that I was providing before. And this is because we might find models like the one that we have in the picture here, in which the agents, two agents, they really, none of them has any information about the truth value of P. You can see both of them consider a possibility in which P is true and another possibility in which P is false. It's just that those possibilities in which P is false, even though they are, in a sense, exactly the same, the two possibilities at the bottom, they are being represented with two different possible worlds. So what happens in this picture is that even though none of the agents has any information, really any information about the truth value of P, their distributed knowledge includes P, just because of the definition in terms of the intersection of our relation. So that's some kind of a bug inside the definition of distributed knowledge. And well, one can actually think of several better behaved alternatives for defining this notion of distributed knowledge within the epistemic logic setting. And here there are a couple of references discussing some of those alternatives. And nevertheless, this notion of distributed knowledge, it still has some natural and appealing properties, or nice properties, sorry. One of them is that, as I mentioned before, the associated relation, the connected relation, the one that describes the uncertainty of the group, in fact, it seems quite natural. It seems quite natural to say that they, as a group, they are going to consider one world as a possibility if and only if nobody has been able to rule that one out. That matches the idea of indistinguishability as the essential part of the models. Because of this, because of the fact that we have a relation for the distributed knowledge of the group, then we can define the modality for distributed knowledge, and that one turns out to be a normal modality which has the same properties as the modality for individual knowledge, or at least the basic, or at least the same basic properties. And finally, if one wants to add additional properties to the notion of knowledge of distributed, to the notion of distributed knowledge of a group, the only thing that one needs to do is to add those properties to the knowledge of the individual members of the group. If we can do that, if we do that, then the notion of distributed knowledge is going to inherit all those properties from the individuals. So that's me a little bit justifying the use of distributed knowledge in this work. And now precisely to the kind of epistemic logic language and so on that we are going to use, we rely on a language that extends the propositional one with the modality for distributed knowledge. We don't really need the modality for individual knowledge because that one can be defined as an abbreviation of the distributed knowledge of a singleton agent, or a singleton set, sorry. The semantic interpretation of this distributed knowledge modality is the one that I just described before. The agents have distributed knowledge of phi if and only in a given pointed model, if and only if in all the points that they can reach from that evaluation point, phi is true, by means, of course, of the relation for their distributed knowledge. And another couple of definitions that will be useful a little bit later. First of all, given a model and a formula, we can define the set of worlds of that model in which the formula is true. And second, given a model and a formula, we can create a partition of that model containing at most two cells, one of them containing all the worlds in which the formula is true, and another one containing all the worlds in which the formula is false. Some basic results, some results that are already known in the literature. There is an axiomatization for this language, and besides the propositional part, there are three essential properties of this notion of distributed knowledge. First of them is that it is closed under modus ponens, the famous axiom K for this modality. The second one is the fact that it contains all the validities. This is the famous generalization rule in modal logic. And finally, the one that is specific for this notion of knowledge is monotonicity in the set of agents. If a group of agents has distributed knowledge that phi is true, then bringing more people to that group will not change that fact. They will still have knowledge about phi. Another notion that is going to be important, concept that is going to be important, relates to the expressivity of the language that we are discussing. This is because we will discuss different languages in a second, and we would like to compare their expressivity. And for that, something that one typically does is to look at some structural form, some structural semantic relationship between two pointed models that holds if and only if those two pointed models agree in the truth value of all the formulas of a given language. In the case of basic epistemic logic and in general modal logics, this notion is that of bisimilarity, meaning that if we have two pointed models that are bisimilar in that classical sense, then that happens if and only if those two pointed models agree in the truth value of every formula of the basic modal language. Here we have a different language, so we need a slightly different notion of bisimilarity, and this is the one that I'm presenting here. This form of bisimilarity, which is called collective bisimilarity, holds between two pointed models if and only if there is a relation connecting the two pointed models, a relation that we call collective bisimulation, and this relation satisfies three important requirements. The first of them is every pair of points that are connected, they satisfy exactly the same atomic propositions. The second one is if you have 2 points that are connected and one of them has a successor by means of the distributed relation for a group G, then the other point of the pair, they also, over there, we can also find a successor by means of a relation for the same group. And those successors, they are connected by this collective bisimulation. That's the fourth condition. And then the back condition, which is only the mirror image of the fourth one, which is now if the second point has a successor by means of the relation for some given group, then the first one also has a successor by means of the same relation, and both points that we can reach, they are connected by this bisimulation. In particular, we say that 2 pointed models are collectively bisimilar if there is a collective bisimulation connecting the evaluation points. And this notion is important because well, we have these two results. If two models are collectively bisimilar in this just described sense, then they agree in the truth value of all formulas in this language with distributed knowledge. And if the models agree in the truth value of all those formulas, and the models happen to be image finite, meaning that every point has only finitely many successors, then the 2 points should be also collectively bisimilar. So up to image finiteness, the notion of collective bisimilarity characterizes the expressivity of our language. That's the setting. Those are the basic tools that we want to discuss. And then let me go now, finally, to discussing actions of communication. Let me also check quickly how is that I am doing on time. We want to be sure that we have enough time. I think we have enough time to discuss what I want to discuss. So first of all, just a quick reminder, there is already a famous action that has been discussed in the literature through which agents receive information. It's just that in this action, the one called public announcement, or the way I like to call it observations, the information comes from the outside. Is somebody outside the model the one that is providing information to the agents in a truthful and a fully public way? But then that means that the agents might receive information that none of them, or none of them even as a group, might have had before. What we want to do, sorry, this is just a repetition of some things that I already mentioned. Through this information, there is an external source giving the information to all the agents in a public and truthful way. And there is a very natural way of representing that action within epistemic logic. And it is just, since everybody is getting to know, is receiving the information, since everybody is getting to know that a given formula is the case, then something that we can do is just get rid of all those possibilities in which the formula that is being announced as true happens to be false. We can just get rid of them because, well, no agent is going to consider them as a possibility, but also nobody will think that somebody else will consider that as a possibility, given that the information is shared in a fully public way. Once again, what I want to discuss here is an action through which the information that is being exchanged, the information that the agents are sharing or receiving, sorry, comes from agents inside the model. And this is not the first time that such an action is explored in this epistemic logic, dynamic epistemic logic setting. There are already 3 proposals, or at least there are 3 proposals that I know that deal with this kind of communication. First of them, from 2010, Alexandra Baldak presented an action through which one single agent shares everything that she knows with everybody in a fully and public way. A little bit related but slightly different, in 2017, Thomas Agotnes and Yi Wang presented an action through which a group of agents share everything that they know, but they share it only within themselves, meaning that members of the group will receive this information, they will receive everything that is being shared, but members or agents that are not in the group, they will not receive this information. But nevertheless, they will see that there is some communication happening. So this is the kind of action that is analyzed in this second paper. And from a slightly different perspective, instead of thinking about agents sharing information with others, Alexander Baldak and Sonja Smets, they studied in 2021 an action through which one agent or a given agent reads information from others. This perspective of is not the agent that is sharing her own information, but rather some agent reading somebody else's information, allows you to discuss things as doing this in a public way or in a secret way. For example, hacking can be understood as me secretly taking information from some other agent. Well, they discuss all these and some other issues in their 2021 paper. So to warm up towards what I want to discuss today, I want to first discuss an action, a simpler action through which some agents share everything that they know. And for this, the first thing that I'm going to do is to tell you how, given a model representing a current situation, we build another model, potentially a different model, representing the situation after, again, some agents share everything that they know with everybody. So the new model is built in the following way. We take an initial model as the one that we have on the bottom left, describing an initial situation. Suppose that S is the set of agents that are communicating, which in the case of the example below is only the agent A. The model that we get after this action takes place, first of all, has exactly the same domain, so the same worlds will remain. Each one of those worlds is going to have exactly the same atomic valuation as before, so the worlds are going to represent exactly the same situations. And the only thing that might change is the indistinguishability relation of the agents. And when it changes, it's going to change in the following way. The indistinguishability relation, the new indistinguishability relation of each agent is going to be the intersection of her previous indistinguishability relation and the relation for the distributed knowledge of the people that are communicating. This is another way of saying after the action takes place, one agent AI is going to consider one world as a possibility if and only if she considered it before as a possibility, and also none of the agents that are communicating can rule that possibility out. In terms of a picture, maybe a little bit easier to understand, what will happen is that the only arrows that are going to survive are the arrows that contain labels for every single agent that is communicating. And they will remain because, well, they cannot be distinguished by any of the agents that is communicating, and therefore they will remain there. In the case of the example that we have here at the bottom, that means that since A is the only agent that is communicating, the edges that are going to survive are, first of all the reflexive ones, because they contain the label A. It will be also the ones connecting the world at the top with the two worlds in the middle, that those two arrows, or in fact 4 arrows because they are bidirectional, those 4 arrows are going to survive. And so will do the arrow connecting the two worlds in the middle. On the other hand, the 2 arrows at the bottom, they are going to disappear because, well, A is the one sharing her information, or more precisely in this kind of setting, letting everybody know which are the situations that she already discarded from each given one. So in a sense, A is telling everybody, look, I know, or I can, or maybe some of you cannot distinguish between this word at the middle left and this word at the bottom, but I can distinguish between them. So I'm communicating you that information. You can distinguish between them, and that is what the agents will do. This is the way in which we create the model after this action takes place. And in order to reason about the effects of this action or the properties of this action, what we do is we add a modality. This modality that we have here on this left-hand side is intuitively understood as after the agents in S communicate everything that they know with everybody, phi is true. And such a formula is going to be true in a given pointed model if and only if in the very same point, but in the new model, in the model that we get after the operation that I just described, in that new pointed model, phi is the case. Okay? A couple of just quick things. You might see that I'm using these angular brackets that might resemble some form of a diamond for this modality of after the agents communicate everything that they know, phi is the case. You can also define the dual one, which will have then some kind of box-like parentheses. But even if we define it in the standard way as the negation of the diamond, the negation of the formula, it turns out that these two, the box and the diamond version of this modality, they are semantically equivalent. And this is just because the operation that we are defining is actually a total function. We can apply the operation to any model that we can think of, and every single time we will get exactly one model. So using diamonds or boxes doesn't make any difference. They both have exactly the same semantic meaning. One example about this, again, simpler version of what we want to discuss. In the picture on the left-hand side, what we have is a model in which we have 3 agents, A, B, and C. Each one of them knows the truth value of one atom, P, Q, and R, respectively, without knowing anything about the truth value of the other 2 atoms. In particular, agent A knows that P is true, but she doesn't know whether Q is true, meaning she doesn't know that Q is true, and she doesn't know that Q is false. She doesn't know Q's truth value. And the same for R, she doesn't know whether R is true. On the other hand, then agent B knows that Q is true, but she doesn't have any information about P or R. Finally, C knows that R is true, but she doesn't have any information about P or Q. That means that then if they were to share all their information, then they would know as a group that the conjunction P and Q and R is true. So let's see what happens after only two of those agents communicate, A and B. First of all, let's get the model. And again, we can follow the intuition that I mentioned before. The worlds and the evaluation, those remain the same. And the only thing that might change is in the indistinguishability relations. And the way that they will change, or they might change, is the only arrows that we are going to preserve are the ones that have labels for everybody that is communicating. So this is the model that we get after A and B communicate everything that they know. And once again, why is that, for example, this arrow with label A and C would disappear? Well, because B can distinguish between those two worlds and B is communicating. So then the other agents will get to know that they can distinguish between those 2 points. On the other hand, again, why is that this arrow with label A and B doesn't disappear? Well, because the only one that can distinguish between those two worlds is C, but C is not communicating. So A and B will not get any information out of this. As a result, meaning in the new model, we can see, as we might have expected, that for agents A and B, they both get to know that the conjunction P and Q is true. Each one of them had already one atom, and they got from the other agent the truth value of the other atom. And nevertheless, they still don't have any information about the truth value of R. C, on the other hand, is the one that benefits the most in this scenario because she got the information, all the information from A, all the information from B, and she didn't need to share anything. So now she knows that the conjunction P and Q and R is indeed the case. A couple of properties from this action are the following. First of them is repetition is irrelevant in this setting, for this action. If the same group shares everything that they know once, then doing it again will not make any difference. Second is if we have two groups sharing everything that they know in a row, then actually the order in which they do that, that's completely irrelevant. We might as well change the order and we will get exactly the same result. And finally, if we have two groups sharing everything that they know in a row, then we can collapse these two steps communication action into one single communication action in which it is the union of the groups which shares all that they know. So that's this very basic, somehow basic, but simpler action through which some agents share everything that they know. And now we can go into our main goal, which is this action through which some agents share only part of what they know, this partial communication idea. And again, the idea is the following. We want for the agents to share only part of their information. This might be useful in different settings. For example, one in which sharing everything that you know, well, is not possible because of limitations on the communication channel, or maybe other settings in which you don't really want to share everything that you know because there might be people eavesdropping through the communication channels and you don't want for them to get all your information. You only want to share bits of it. And if we want to make this idea precise, of course, the main point is to define what is the information that each one of the agents is going to share, what part of their information they will share. And this can be defined in, well, I can imagine many different ways. One particular case could be, for example, to say that each one of the agents is going to share just a random part of what they know, as long as it is not everything. What we do here is something slightly different. What we want to do here is to fix something that we call the topic of the conversation. So intuitively, there is a topic on this conversation that is happening. And when this conversation, this communication happens, the agent will share everything that they know about the truth value of this topic, which is going to be understood or represented by a formula. And I want to emphasize that they really want to discuss, or they are really discussing the formula as a topic, meaning they are interested in everything that allows them to get to know the truth value of the formula. versus understanding this formula as the subject, for example, in which case they might discuss only whatever they have supporting the truth of the formula, not the truth, not finding the truth value, but only supporting the truth of the formula. Again, here what we want to do is understand this formula as the topic, meaning that whatever is relevant for getting to know the truth value of this formula, that is what the agents are going to share, whatever that they have, of course. And then let's go to the main part of the whole idea, which is how is that we define the model that we get after this form of communication takes place. And the idea is the following. First of all, the model that we get, once again, contains exactly the same words, and the words reflect or denote exactly the same valuation as in the original model. The difference is that now we want for the agents to share only part of what they know, and again, only what they know about the truth value of a given formula. So to do that, we will do the following. This is the formal definition, but let me instead of going into the formal details, let me try to tell you what the definition is supposed to do. First of all, we take that formula which is defining the topic of the conversation, and we use it to create a partition of the words in the original model. This partition then, again, might give us up to 2 cells, one of them containing all the words in which the formula is true. In the example here, this partition at the top contains all the words in which P, the topic of this conversation, is true. And at the bottom, we have all those words in which P, the topic of the conversation, is false. And what we are going to do with these partitions is arrows within those partitions are going to be protected. They will never be deleted by this operation. Why is that the case? Because arrows between, or arrows inside the same partition, they do not concern the truth value of the topic, because they are connecting words that agree in the truth value of the topic. On the other hand, arrows going across partitions, they do concern the truth value of the topic, because they are telling you that the agent cannot distinguish between words that disagree in the truth value of the topic. Those arrows, the ones across cells, those are the only ones that might be deleted. And they will be deleted exactly in the same way as before, meaning among the arrows that are connecting different cells, the ones that will survive will be the ones that contain all the labels of the agents that are communicating. So essentially the same idea as before, just with some arrows being protected because they are not about the topic of the conversation. In the case of this example, what will happen is, once again, the arrows inside the cells, they will remain as they were before. They will never be deleted. The ones that might be deleted are the ones across the cells. And in this particular case, in which it is A, the one communicating, the arrow connecting the word at the top with the word at the middle right is going to remain because it contains the label A. The arrow containing the 2 words in the middle will remain because it contains the label A. But the arrow containing the word at the middle left with the word at the bottom, that one will disappear because it is an uncertainty that agent A can discard, and it is about the topic that agent A is talking about. So this will be the resulting model. Just as before, we can also introduce a modality that allows us to talk about and reason about the effects or the properties of this communication action. And we define the semantic interpretation for this formula in a similar way. We say that after agents in S share everything that they know about topic chi, phi is going to be the case in a given pointed model, if and only if in the same point, but in the new model, phi is indeed the case. And once again, just as before, I'm using here these angular brackets that resemble a diamond. But if you want to define the box version of that modality in the standard dual way, then you will find out that those 2 modalities, the box-like and the diamond-like version, they are semantically equivalent. Once again, because the operation that we are defining is actually a total function. It works, it can be applied to any model, and it returns every single time one single model. Three examples just trying to illustrate which kind of things we can describe with this partial communication action. The three of them starts from the very same situation as before, three agents, A, B, and C, each one of them knowing the truth value of an atom P, Q, and R respectively without knowing anything about the truth value of the other two atoms. In the three cases, the agents A and B are the ones sharing information just as before. It's just that in this case, in each one of these cases, each one of the columns, they talk about a different topic. On the leftmost case, they talk about a conjunction P and Q. So which one is the resulting model? Once again, the first thing that we do to obtain that model is create the partitions, putting together on one side the worlds in which the conjunction is true, and on the other side the worlds in which the conjunction is false. Once again, in the resulting model, arrows within cells are going to remain the same. They are not going to be affected. And arrows across different cells, they will remain as in the original model if and only if they have the labels for all the agents that are communicating. In this case, this is the resulting model. Once again, the arrow connecting the word at the top with the word at the middle disappear because B is able to distinguish between those two worlds, and more importantly, this uncertainty is about the topic that is being discussed. And in a slightly similar fashion, then the arrow A and B with A and B at this left-hand side is going to remain. That's because, well, in this case, it's because it's not part of the topic under discussion. So those arrows will remain there. On the other hand, if the agents were talking about a conjunction P and R, then we create the partition and then we apply the operation as described. This would be the resulting model here. You can see the arrows connecting the world at the center with the worlds at the bottom, they both disappear. Why? Because B can distinguish between those and because those arrows are about the topic of the conversation. In particular, this example shows you that the operation might not preserve transitivity. You can see how there is a sequence of arrows from the middle to the top with A and then to the bottom left with A, and yet we don't have an arrow connecting the center with the bottom left. So that is one of the technical reasons why we don't impose the transitivity requirement in these models. The operation will lose that property, and then we will have something that doesn't match. Well, technical definitions, we will have an operation that changes the very core of the notion of knowledge that we are talking about. This very same example also shows that the operation doesn't preserve Euclidean relations. Again, the very same situation with A shows that. And another example on the left-hand side, on the right-hand side, again, A and B communicating, but now talking about a different topic, the conjunction Q and R. We create the partition, we create the new model. So just some quick examples about the kind of things that can be represented in this setting. Now, properties of this setting. Important properties is, first of all, this operation of partial communication, meaning talking about a given topic, is not a generalization of the operation in which the same set of agents talk about or share everything that they know. This is simply because if that were the case, then there should be a formula such that in every possible model would represent or would be the fact that the agents share everything that they know about that formula would be equivalent for them to share everything that they know in general. And there are no such formulas. Some formulas in some particular cases might be such that when an agent shares everything that they know about that formula, the agent is in fact sharing everything that she knows. But that formula doesn't need to be the same across all the possible different relational models, possible words models. Two more important properties, or rather lack of properties, is that in this setting, repetition actually matters. If a group shares everything that they know on a topic, and then they do it once again, we might get different results from what they got after sharing the first time. In this setting, also, the order of sharing matters. If you have a group talking about a topic and then another group talking about another topic, the order in which they do that might make a difference. And other two lack of properties, if we have two different groups talking in a row about the same topic, you cannot collapse that into a single communication action in which the union of those groups talk about the same topic. And analogously, if you have the same group now talking about two different topics in a row, then you cannot collapse that into one single action in which the group talks about the conjunction of those topics. Then a couple of results, technical results of this partial communication setting. The first of them is that bisimilarity, collective bisimilarity, is still good enough to guarantee that two pointed models will agree in the truth value of all the formulas of this extended language, including the new modality for partial communication. Another result, technical result that we have is an axiomatization based on reduction axioms, meaning that there is a translation that can take any formula in the language with this partial communication modality and will produce a logically equivalent formula without that modality, meaning a logically equivalent formula in the basic language that has only Boolean operators and distributed knowledge. And precisely because of the existence of that translation, it turns out that these two languages are equally expressive. That whatever we can express with this additional modality of partial communication, we can also express it with the language that has only Boolean operators and distributed knowledge. The final thing that I want to mention, if I can spare a couple of minutes besides the limit of 45, is now we have this action that represents a way in which agents get information, this communication, partial communication, in fact. It makes sense to compare it in a couple of senses with the typical action through which agents receive information, this time from an external source, meaning the public announcement action. For the sake of fairness, as I was mentioning before, the action of public announcement is typically represented by means of an operation through which we remove words from the model. So if we want to make a somehow fair comparison with this setting in which we don't remove words, we might affect only relations, then it makes sense to define the action of public announcement in an alternative way, one in which only arrows might be affected. And this can be done in a natural way, because at the very end, the core of the public announcement action is you cannot consider, given a situation in which the formula that is being announced is true, you cannot consider now a situation in which that formula that has been announced is false, which means that the public announcement can be understood in relational terms as an operation that only breaks or deletes all those arrows connecting words that disagree in the truth value of the formula that is being announced. And you can define the formula, or you can define a public announcement in that way, and it gives you exactly the same results as what you will get with the standard definition that removes words. As it turns out, the public announcement modality also doesn't add any expressivity to the language, to a language that has distributed knowledge, which means then that the language, our language with the partial communication modality and the language with the public announcement modality, they are equally expressive because they both reduce to the very basic language that has only distributed knowledge. But we can also compare these two settings in a different way, in an update expressivity way. Meaning, if I give you one epistemic model, one relational model, and we know that some public announcement action can transform and produce certain epistemic situation, can we replicate that very same effect with a partial communication action and the other way around? The answer is that, as we might expect, there are some things that can be produced by a public announcement that cannot be produced by partial communication. Particularly if you have two agents and none of them can distinguish between a world in which P is true and a world in which P is false, then certainly an external public announcement can get them to know that P is true. But that cannot be achieved by partial communication because, well, none of the agents have any information that can provide to each other such that they can distinguish between those two worlds. Interestingly enough, there are also situations that we can obtain via partial communication that cannot be obtained by public announcements. And here, the example that we show is one through which, via partial communication on the model on the left-hand side, if the agents A and B communicate on the formula P if and only if Q, then we get the model on the right-hand side. But this effect can never be achieved by a public announcement, simply because of the fact that a public announcement preserves transitivity relations, preserves the transitivity of relations. And as you can see, this operation does not. So that's everything that I have to say about partial communication. Once again, there is a bunch of things here about arbitrary partial communication, but maybe I can just try to close quickly. The idea behind this partial communication is some agents share part of the information, and what they share is defined by a formula that is understood as the topic of the conversation. By adding this formula, this topic of the conversation, we bring back some of the dynamic features of public announcement, meaning repetition matters, order matters, and so on and so forth. Intuitively, as we discussed, this form of update is incomparable to the update that we get out of a public announcement. It can do some things that the public announcement cannot do, but also cannot do some things that public announcement can. And arguably, this could be a more natural way of representing communication between agents. This is a summary for the part that we didn't discuss. Things to do, ongoing work. We have some complexity results. We would like to get a little bit more. We would like to find more concrete applications of this idea. And maybe we can try to find some transitivity preserving variation of the operation in case one wants to work with a notion of knowledge that requires transitivity. We can also extend the framework in at least a couple of ways. One of them is adding formulas for common knowledge, a notion that is also important for groups of agents. Discussing topic not as a single formula, but rather as a set of them. And maybe going into beyond sharing truthful information. What if agents share information that they don't have? How can we do that? How can we represent that? That's it from me. Sorry for the additional 4 minutes, but thank you very much for hanging in there, and I'm happy to answer any questions you may have.